Good morning, everybody. In the next 20 or so minutes, I'm going to try to convince you of a new optimization goal that we can try to achieve for a new type of memory technology that is coming out. Specifically, we're going to be focusing on byte-addressable non-volatile memory and how to optimize for power and wear, not by reducing the number of writes necessarily, but by reducing the number of bits flipped by those writes. And I'll talk about some of the strategies we used and show a little evaluation. Okay, so byte-addressable non-volatile memory is coming. A number of vendors have discussed their plans to release a byte-addressable non-volatile memory that fits on the memory bus, right, in a DIMM slot, right? So the processor can access this persistent memory via normal load and store instructions, right? This introduces a number of new challenges and opportunities, right? We have opportunities for redesigning the way that we build our systems to try to take advantage of this, and we also have new challenges. For example, dealing with consistency issues, right? So you have to deal with this problem where if you are in the middle of doing this fine granularity update to your persistent memory and the power restarts, and then you come back up, you have to now worry about the kind of fine granularity consistency problems that can crop up. Right? There's been a lot of research into this technology and into ways of using it, right? And a lot of the times that focuses on things like reducing writes. And that's great. Reducing writes is really important for performance and to make consistency things easier, right? But it's not the only optimization target that we have, right? If we zoom in for a moment and look at why those writes are expensive, it's because in a technology such as PCM, for example, when we do a write, we're replacing an old value with a new value, and some of those bits have changed, right? In PCM, you have to update a cell structure by physically melting and resolidifying the contents, right? The controller can make an interesting optimization here. Because writes to a particular cell are so much more expensive than reads, the controller can actually read the cell first and decide, oh, it's already the value it's supposed to be, and not update it. This means that the writes are not necessarily all uniformly expensive. It depends on how many bits flip within a particular write, right? This has obvious implications for wear, right? Because if we're constantly flipping certain bits, right, then those bits are going to wear out more than others, and the entire word becomes unusable, right? So there are hardware techniques that have already been researched that allow you to spread out those flips throughout a particular region of memory, right? But that means that if we actually focus on reducing those bit flips, we can overall reduce the wear of our medium. So that's not the only thing, though, right? So check this out. We did this back of the envelope calculation, right? We took a number of papers we surveyed a number of papers that discussed the power consumption characteristics of certain non-volatile memory technologies, right? And we plotted their power consumption as the number of bit flips per second increases. And we saw this relationship here, where we see that for DRAM, it's basically a flat line, right? There's this high refresh cost here, right? But ultimately, the number of bits flipped in all of your writes doesn't really affect it. It affects it a little bit because you're actually writing, right? But there's not a huge impact. So you wouldn't optimize for bit flips because it doesn't save you anything. But for PCM, right, that line is much steeper. This means that if you actually reduce the number of bits that you flip, you can significantly impact the power consumption of your technology. So given that we want to try to reduce bit flips, right, that leads to a couple of interesting questions. The first one is, do we do it in software and hardware? Well, the benefits of doing it in hardware are that it's a much more general application, right? Because if I'm doing it in hardware, it works for any kind of software I'm running. It works constantly. It has this disadvantage in that it doesn't take advantage of the additional semantic information that software might know, right? If I know how my data structure is laid out, perhaps I can change it a little bit to try to reduce the number of bit flips overall. And there has been previous work studied on doing this kind of stuff in hardware, right? But it had some limitations in that you need to re-encode the cache lines as they're coming in, so you have to store additional bits, and that can potentially waste some memory. Right? The second question is, how hard is it to actually reason about bit flips? Is this something that we can do? So we did some previous work that studied certain data structures under different characteristics of their implementation or different design choices, right? And we noticed one thing. The first data structure that we tried, it turned out to be a hash table, based on small modifications to the implementation details and the design choices, we were able to dramatically change how the bit flip characteristics of that data structure, or what the bit flip characteristics of that data structure was, right? So this means that this is actually something that we can try to do, right? We also noticed another interesting thing that's going to crop up a little bit later on in this talk. There was this interesting write bit flip inversion behavior, where a common wisdom might be, well, if you reduce the number of writes, then you'll reduce the number of bit flips as well. That makes sense. It turns out that's not always true, right? We observed that write flip inversion in our previous work, and it'll come up a couple of times here later on in this talk as well. Okay, so then finally, how do we actually design data structures to reduce bit flips? Right? Given that we want to do this, and given that we can reason about it, what are some of the strategies we might use, right? So obviously, right, we've already answered, we're going to focus on software. How hard is it to reason about bit flips? Turns out it's not too hard. And obviously questions like, can we do this? I mean, since I'm giving a talk, I'm going to answer yes to that, right? So one other thing that I want to point out here is that we focused on data structures and not the data itself. The reason for this is because the data itself has to be written anyway at some point, right? You might decide you could re-encode that data to try to save bit flips, but you might want to do that in the hardware level instead. So our software techniques and hardware techniques can work in tandem, right? Often when you write a bunch of data, you write it once and you update pointers to it, hence the data structure focus. Okay, and I just wanted to point out, this is sort of the tip of the iceberg here. We focused on some data structures, and we focused on developing a framework that allows us to evaluate a measure of goodness for figuring out how our data structures behave. But there's a lot more work that can be done here. Okay, so let's talk about the details of some of these, right? So we decided to focus on 3 data structures, right? Our previous work was mostly on observation, and so this work is actually targeted optimizations to try to improve the bit flip characteristics of particular structures, right? So the ones that we did was we did XOR linked lists, and we looked at RedBlack trees, and that applies to any kind of binary search tree in general, and we also looked at hash tables, right? We used two strategies throughout this. The first one was storing pointer distance instead of absolute value, which I'll talk about more. And the second one was to store additional unused bits to indicate that a value is actually 0 when it might not be. Okay, so let's get into this. XOR linked lists, right? So this is actually one of my favorite data structures. I think it's really clever. So a traditional doubly linked list, you store 2 pointers, next and previous, right? And that's great, but if you could XOR the next and the previous value together, you could only store 1 pointer instead of 2. Because what I'm essentially doing by XORing together next and previous is I am storing the pointer distance from the previous node to the next node, right? So if I have 2 adjacent nodes in an XOR linked list, I can traverse in either direction. Because let's say I have node A and B, right? I can XOR A's address with B's X pointer value, and I get C. And so I can traverse forward, I can traverse backward. Obviously, there's some limitations to this. Given a single node into this list, I can't do anything, right? But these are trade-offs that you might want to make, right? So, okay, why is this good for bit flips? Well, first of all, it reduces the size of the node, but that's not really the reason. The real reason is because of what pointers actually look like, right? So I called malloc twice on my machine. I got back 2 pointers, and there they are. There's a lot of set bits in those pointers. But if you XOR them together, you end up with very few bits actually set, right? So if you run a lot of operations on a linked list, right, and if you store the XOR between 2 pointers instead of the pointers themselves, then you actually save a lot of bit flips because the memory is already 0, and I'm writing things that are mostly 0 to it. Okay, so an obvious application of a linked list approach is to a hash table where we do chaining to resolve collisions, right? So we can use the XOR trick in a hash table here, except that in a hash table you wouldn't store a doubly linked list because you only need to iterate once, forward through it. So instead of storing next and previous XOR together, we store next and current node XORed together, right? And So that works pretty well. You can still traverse the list fairly easily, and it still has the same effect of storing a pointer distance value. The second thing that we did is to store this additional bit. It's not really an additional bit. It's using a bit that would never be used, right? So the least significant bit of the next pointer is always going to be 0, right? So we can use that to indicate that a particular bucket or entry in a chain is the last one, right? Without having to overwrite a value that was already there, right? So this also saves bit flips, first of all, because you don't have to overwrite. You don't have to set a value to 0 when you want to delete it. And because if you come in the future and you write something there, now it's already, it has a previous value, and now you're overwriting it with a new value, and you might be able to save some bit flips there. And this approach works not just for this next pointer, but it works for any sort of situation where your least significant bit or one of the bits in your word isn't used. OK, so beyond a direct application of these of XOR linked lists, we can also extend them, right? So we built an implementation of a RedBlack tree. This works for any real binary search tree structure, where in a standard RedBlack tree design that uses a 3-pointer approach, right? You have a left pointer, a right pointer, and a parent pointer, right? And you can traverse the tree up and down. However, if you XOR together the parent and the left pointer and the parent and the right pointer, now you can store LX and RX, right? Only 2 pointers instead of 3. And you can still traverse the tree up and down, right? You could traverse down. That's easy enough because I have a parent and a current node. So I XOR together LX with the parent pointer, and I get the left. And similar for the right. I can traverse up the tree as well. It's a little bit harder because if I have a child and a current node and I want to get to the parent, I need to know which child I am, and I might not know that. But I can use the ordering information in the tree to figure that out because I know which node I am and I know what value I am, right? So I can still traverse up and down. OK, so those were the 3 data structures that we looked at, and those were the strategies that we chose to use. So we decided to evaluate these. And we wanted to evaluate them under 3 criteria. The first one is how difficult was it to implement these structures with this new requirement of XORing and additional stuff? And it was relatively easy, actually. There was only a couple of additional bugs that were introduced in the process of writing the XOR version of the data structure compared to the standard version, right? And it didn't increase the code size significantly. I mean, there's a couple of additional things you have to do. In the hash table, when we're storing that additional bit to indicate deletion, you have to do an additional check, an additional test to see if that's set or not. That's a stupid thing to do unless you're trying to reduce bit flips, because now we have 2 ways of indicating that something's empty. What's the point of that, right? But when we're trying to reduce bit flips, it helps. So code was relatively straightforward. So the next 2 important ones are what are the actual bit flip characteristics, of course, right? And what's the performance impact? Because if we have to suffer in terms of performance, we might not want to do as many of the strategies that we just talked about. OK, so let's get into this. Our prior work counted bit flips in data structures, but it did so by manually instrumenting the code. And we view this as a limitation because that doesn't allow us to take into account the effects of all the different layers between the software and the actual memory controller, like caching, right? Or compiler optimizations. If I'm manually instrumenting the code, that's affecting the compiler's ability to optimize the code, right? And a whole host of other reasons why that might not give faithful results, right? So what we did is we took a full system simulator, Gem5. It's a cycle-accurate system simulator. And we patched it so that it would count the bit flips of incoming writes at the memory controller level, right? And it would report the value at the end when the run was finished. So Gem5 was really convenient because it has this ability to emulate Linux system calls. So you can just build yourself a data structure and write a test harness and run it on the system simulator, and it will work. And this is also really convenient because it allows us to play with different parameters like cache size and cache levels and things like that. And I'll talk about that as well a little bit later on. So yeah, OK. So this is sort of a warm-up slide. So this is the basic results of what we get when we call malloc repeatedly, right? So the first thing I want to point out here is that this was a really common picture that came out of the simulator when we ran most of our data structures, right? It was this sort of repeated pattern where at the beginning there was a warm-up period where the caches had some effect, and then later on the trends became linear or just a little bit more than linear, right? So here we can see that calling malloc with 40 bytes, for example, there's a little bit of nonlinearity at the beginning, and then eventually it becomes linear. Same with 48. There's a really interesting thing, though, that happens between 40 and 48. Initially, 40 is cheaper in terms of bit flips, and we believe that that's because it's smaller, and so you are doing fewer writes overall, right? And maybe the cache is sort of absorbing more of them at first. And then eventually, 48 starts to win out, right? Even though it's bigger. And so our guess as to why that's happening is because 48 might be a little bit nicer in terms of alignment for the allocator, right? So this is, of course, heavily dependent on the allocation system. OK. So let's look at the first data structure, the XOR linked lists, right? So here we see a significant improvement in the number of bits flipped, right? The doubly linked list has, upwards of 10 bit flips per operation, whereas the XOR linked list is dramatically lower than that, right? So this is a very straightforward data structure that we can write that gives us a very dramatic saving. If you look at the number of bytes written and the number of bytes read, they don't actually change significantly. And it's partly because the node size, although smaller for the XOR linked list, ended up not being any smaller because of the allocation strategies, right? But this is already hinting at that bytes written and bit flip inversion, right? Where we happen to see this here where the number of bytes written didn't change, but the bit flips dropped dramatically. So we can do, these two things are at least independent, or can be at least independent, right? And the number of bytes read is also the same. It was actually really interesting. If you look at the actual code, the number of bytes read is actually more overall inside the code. But it was all of the additional reads that you would make were exactly the ones that were already in the cache. So the cost of doing additional reads in an XOR linked list is actually very cheap. OK. Let's talk about the next data structure, the hash table. Here we see not as dramatic an improvement, right? But we do see an improvement. The reason why this is not as dramatic as the XOR linked list is because one of the most significant strategies here is using the pointer distance strategy instead of absolute values. The thing is, for a hash table, the common case should be that the chains are short, right? So you don't actually use that strategy particularly often, right? However, you still see an improvement, right? It's non-zero, and that's actually still a not insignificant improvement if you consider how this affects wear and power consumption, right? And as we'll see a little bit later on, you get this for free, right? So that's a little spoiler for the performance section, right? OK, so for RedBlack trees, right? Again, we see a significant saving in terms of bit flips over there on the right. I guess left for you guys. We see about half, right, the bit flips compared to a standard implementation. So I should explain the key here. So XRBT is the XOR RedBlack tree that we implemented, right? The 2 pointers approach, or the 2 pointers from the 3-pointer approach. XRBT big is that exact same code, except we artificially increase the size of the node to the same size as a standard RedBlack tree node. We wanted to do this because we wanted to control for the size of the node in our experiments, right? And then RBT is a standard RedBlack tree implementation, right? So yeah, we see the significant savings. But here again, we see that write bit flip inversion, right? If you look, the number of writes made by XRBT, or the number of bit flips made by XRBT, is more than the number of bit flips made by XRBT big. And if you remember back to the malloc test, that's because it happens to be that XRBT's node size is 40, and XRBT big's node size is 48. So we see that, right? A slight impact. But if you look at the number of bytes written, it's the other way around, right? The number of bytes written by XRBT is less than the number of bytes written by XRBT big. And again, that makes sense because the nodes are smaller, and so that you can fit more into cache lines. OK, so the next thing that we looked at was the effects of a layer 2 cache. right? So what happens if we put a layer 2 cache in front of our system and observe the direct effects of that? So based on this is the same experiments with the XRBT and the RBT, right? Except that now we are showing you the sort of initial warm-up period with the cache, right? There is no dramatic effect in the long term, right? That's the big takeaway from this. Initially, the cache absorbs the writes, but eventually, those writes start to make it out to memory because the cache fills up and because, all that kind of stuff. So eventually, you see the cache lines, like the green sort of Y symbols there, eventually meet the blue pluses, right? And then they go linearly together from there on. This happens even if you play with the size of the cache, right? So here we see that it's the same experiments. It's just that now we've done, I think this was XRBT with different levels for L2. We had no L2, 1 megabyte, 2 megabytes, 4 megabytes. They eventually all meet at the top, and they go from there, right? And the delay, the warm-up period, is exactly as long as you would expect for 1 megabyte, 2 megabyte, 4 megabyte. So let's talk about performance for a minute, because we want to have not a significant performance impact. So here we see the performance of RBT and XRBT. So it's interesting. XRBT is actually faster than a standard RedBlack Tree implementation, even though we have to do those XORs. And the reason for that is because you actually do gain in performance from having a smaller node size, right? So B is the benefit you get from having a smaller node size, and the A interval there is the cost of the XORs, right? It's a little bit more dramatic here for random insert, and lookup looks very similar to this pattern. And so then finally, this is the performance of the hash table. There is very, very little impact. Those are actually within the error bars of each other. So there's very little impact on the performance for adding the XORs. Again, that makes sense because the chains are short, so we're not doing that as much. OK, so in conclusion, studying bit flips really matters, and it's something that we can do. Right? We've shown in this work that you can actually take some strategies and you can actually target this optimization specifically and make progress. Right? So we can design around bit flips, and we should do it. Right? We need to focus on the bit flips specifically. Right? This bit flip write inversion that we keep observing keeps cropping up. And our sort of hypothesis for this is because while you reduce your writes, obviously reducing writes is really important for a lot of reasons, performance and whatnot. So we need to do that. But we also need to look at the bit flips directly, because when you reduce the writes, you might be changing the entropy of those writes. And it might not be a linear relationship in that increase of entropy versus the decrease in writes. Right? And so we believe that's what we're seeing in our results. Right? So we need to focus on bit flips as well as writes, and we need to focus on them specifically. And like I said, there's a lot of work that can still be done in terms of looking at the performance impacts and looking at new structures and new algorithms and different algorithms, taking a new system that's specifically designed for BNVM and really trying to put this optimization in it from the ground up would be really, really interesting to see. Right? And looking at real hardware as it starts to come out. What are the actual impacts? What are the actual characteristics of the hardware and all that kind of stuff? And that's all I got. I just wanted to point out one thing. We have this repo where we're going to be posting the patches and posting the scripts and things like that that we use to process the results. It's not quite up yet because I want to finish writing up some of the documentation for it so that it's a little bit easier to navigate. All right. Thank you very much.
Hi. Just a couple of quick questions. So this software optimization depends on there being a hardware optimization, right? That the controller reads and only modifies the bits that need to be modified?
Yes, it does.
Okay, and do you know that they will do that?
There are several papers that we've looked at that discuss doing this and show good results for it. So we believe that this will be a common optimization for these kinds of technologies. Whenever you see a dramatic disparity between the write cost and the read cost, whatever that cost is, be it power or time or wear, right? This optimization makes sense for technologies that can have that sort of low-level granularity of looking at the cells.
Right. The other quick question is, if even one bit has to be flipped, then there's no speed improvement in the write operation, right?
So that's an interesting question, right? That, again, I think that's a hardware, or like a hardware level thing. And that is something that we didn't look at that would be really interesting to look at, right? Because I was thinking about this actually right before the talk, was, let's say that you write a full cache line, 64 bytes out, and half the bits flip, what's the right performance cost of that versus what happens if you write 64 bytes where only one of them flips? I mean, like, you could think about it in both ways. We're like, oh, well, the controller still has to go through every bit. But writing a bit is really expensive in something like PCM, not only just in power, but also in time. So maybe the controller could return back to you much quicker, that information. On the other hand, we'd also see things like, the absorption of things like this by buffering the writes in the memory controller, right, and queuing them there. So, I don't know. I think it really depends on the hardware.
So at the beginning of the talk, you said that the reason that it's interesting to reduce bit flips is two reasons, right?
Yeah.
One was power,
Yeah.
and the other one was wear.
Yeah.
Okay, power I get. You put a graph up there. It's very linear. The fewer bit flips you do, the less energy you use, the better off you are.
Right.
Okay. Wear is more interesting, right? So you just proceeded through the talk and used total number of bit flips as a proxy for reduction in wear. But I think that's probably not really the way it works, right? What you actually care about is what's the number of bit flips for the particular bit that has the maximum number of flips.
Well, sort of.
Right, because when a bit wears out, then the hardware has to do something to compensate for that.
Right.
And the techniques that you did reduce bit flips by, if I understood it right, by mostly the high order bits of a pointer address don't get flipped because things are close to each other in memory, and the low order bits probably get flipped just as much as they would have in the old scheme. So it might not help with wear. So if you look at the distribution per bit.
Yeah. So we do discuss this a little bit in the paper, but I can elaborate. So you're right. The issue is that by doing some of these optimizations, we do actually create hotspots, sort of, in the words, right? Or we move the hotspots around a little bit, right? So that's true. And the reason we focused on total reduction is because, and we do cite several of these techniques, there are techniques that the controllers can use to spread out those writes or spread out those bit flips, right? So like a very straightforward one would be every n writes to the word, you'd shift, right, where you actually store it by 1. And you just do that in a circular shift pattern, right? And so that will spread out those hotspots, right? And that could be very effective. Right, so one of the things that would be interesting to look at would be, combining this work with something like that and looking at the actual wear out of the bits. Unfortunately, we don't actually have the technology yet, so we couldn't do that. But you're right, though. There's another issue, is that that's only within a word, right? So if we wear out a particular word a lot, right, but then the next one isn't worn out, we still see a sort of uneven wear pattern. And one of the problems with this technology is its latency is so low that doing an FTL kind of strategy might be infeasible. Right. So there's a lot of really interesting research there as well that we think would be interesting to look at in tandem with this work. So yeah, that's a very good question. Thanks.
We have time for one more brief question.
I guess that's me.
Sure.
Tom Talpy, Microsoft. Some of these devices, this is really interesting work, by the way, some of these devices are sort of non-linear, right? The more you write them, the hotter they get, the hotter they are, the slower they store. Was that part of your model?
That was not part of our model. The model that we described there was a very back-of-the-envelope calculation, just to get an idea, right, of what the behavior would be. Looking at where that crossover point was interesting. Yeah. But you're right. So that would be something, if we were to extend this model further, we'd have to take that into account. Now, I do think that this work would affect that. I mean, this is speculation.
Oh, definitely. The fewer 1 bits you write, the colder the device gets to stay.
Exactly. So it potentially makes it more linear as you reduce the bit flips. Yeah. That would be another really interesting thing to look at.
Yeah, it would be really interesting to factor that in. I think your curves would flatten out quite a bit more.
Yeah. Thank you very much.
All right.
Let's thank our speaker.